So the standard basis vectors in R2 are I and j. So I, which is this vector 1 0, and j, which is this 0 1. The standard basis vectors in R3 are I, j, and k, where I is 1 0 0 and j is this vector 0 1 0 and k is 0 0 1. And this might kind of feel, or you might find this familiar from your physics or high school math classes. And the standard basis vectors in Rn, and by now you already might have guessed it, are, let's say, E1, which is equal to 1, and then 0 0 0 till n. So this E1 will have n elements, so there will be n elements such that the first element will be 1, and likewise E2 will be 0 and the second element will be 1, and rest of all the n elements, rest of all the n minus 1 elements will be 0. All right. So so basically the standard basis vector EI of the Euclidean space Rn will have all the elements, all its n elements 0 except the ith element. So this is the ith element. So every two-dimensional vector is a linear combination of standard basis vectors I and j. Okay, and you can see why this is the case, right? So let's take any vector u, which has components or elements u1 u2, and you can express u as u1, the scalar u1, right, into 1 0 plus the scalar u2 into 0 1, right? And this is nothing but u1 into the I vector plus the scalar u2 into the j vector. And I and j are special vectors because they have got unit length. So let me draw these vectors here first. So let's say this is 0, this is 1 2, and again here it's 1 2. So the vector I, if we assume that it starts from 0, will be this vector. Okay, and the vector j would be this vector, and you can see that these two guys have length 1, and also vectors I and j are perpendicular to each other. So they are perpendicular to each other. Even E2, so in Rn we deal with the standard basis vectors, and they are called E1, E2, and En. And even in Rn, the standard basis vectors, they have got unit lengths, so their length is 1, and each Ei is perpendicular to Ej, where I is not equal to j. So basically what it means is that each of these vectors is perpendicular to the other vector, and I will prove these properties for standard basis vectors in Rn later on in this course. So right now you can just trust me that this is the case. And also I forgot to add that just like in the case of two-dimensional vectors, we can show that any vector u in Rn, any vector u which belongs to Rn can be expressed as a linear combination of standard basis vectors E1, E2, and En in Rn. So let's say there is any let's say there is a vector u in Rn, like so, and you can of course express this as u1 into 1 and then 0 0 0, so we'll have n minus 1 zeros, plus u2 into 0 1 and then again followed by zeros, plus un into 0 0 0 and there's 1 in the end. And this is nothing but u1 into the standard basis vector e1 plus the scalar u2 into the standard basis vector e2 plus the scalar un into the standard basis vector en.